Oh, welcome to Lecture 61. I'm Dr. Ryan Hayes at Andrews University Chemistry Department, and we're going to talk more about nuclear chemical reactions today, specifically on the kinetics. Radioactive dating, some would call that. Let's get started first with a question. Where does the electron come from in beta emission? What do you think? Is it one of those inner orbitals, 1s, or maybe the a 3D orbital, or perhaps some outer just valence orbital that's there, or maybe the nucleus? What do you think? All right, hopefully you've made a guess there, and the answer is quite revealing. It actually comes from the nucleus. Well, wait a second, you should be saying, in the nucleus, here's the nucleus, there are no electrons. And that is correct. There are nothing but protons and neutrons in there, and the electrons we understand to be on the outside of this guy. So how is it that an electron comes out of the nucleus? Man, electrochemistry is weird. Strange things happen. What's going on? There is an unstable neutron that we write with a 1, 0, and it turns into a proton and an electron. You can see the mass numbers all add up. It's 1 on top and 1 and 0 on the top. Mass numbers on the product side, and then the atomic charge is 0 on the reactant side, and 1 plus a minus 1 there for the products. So a neutron gets converted and shoots out an electron. Really strange. So that's an important process, and it happens, and we just have to get comfortable and used to that kind of thing happening. All right, for my students who may be watching this, you got some like hand-in homework to do in OWL, online web learning, and quiz in there as well, and information about the lab final coming out. I just thought it'd be good to talk about one of the important persons in this radioactive nuclear chemical history, and her name is Marie Curie. You should get to know this lady and know a few important details. She was working on her PhD under the advisement of Henry Becquerel. They were testing this rock, this material called pitchblende, and that's where they would extract and get uranium out of it. But from their calculations and what they could discern and how they understood at the time, it seemed like there was a lot more power, radioactivity there than they were predicting. This gave Becquerel the notion that perhaps there was maybe some different elements in there that were radioactive. So he gave a new assignment to Marie and Pierre Curie to go find this new element that's in there. So he gave them a ton of pitchblende that was secured out of the Ore Mountains, and people have gone into you can go there to this day, and I think you can still see some uranium. And so what's 1 ton? It's like the back of a big pickup truck. So that's a lot. But what they did was work through every single grain of that and dissolve things, wash them with certain chemicals, rinsed, filtered, precipitate, did all sorts of things all through all of that. And she was able to, and being a mother, and they were doing this like in a little shack outside their house. So for 2 years, they worked through all of this, and she was able to extract 0.1 grams, 100 milligrams. It's just a little bit of a powder of radium chloride, a new element. In fact, she got a couple different elements out of there because they had different properties. She discovered a new element and coined it polonium after her homeland of Poland. And it was 300 times more uranium, more active, radioactive than uranium. So Professor Becquerel was correct. And she also discovered radium. And it was a million, and it is a million times more radioactive than uranium. So she wrote up her dissertation on these elements and the work that she did, and she got her PhD. Amazing. So where do all these radioactive materials come from? They are right there. I should get rid of some of this stuff. Sorry about that. All of this comes from the ground. The Earth is very radioactive, and these materials are scattered throughout. And so people, scientists have been trying to pull them together for different purposes. And you can see radioactive elements that are very important are uranium, and it decays down into lead, and potassium turns into argon. Uranium also 238 goes to lead 206, and rubidium goes to strontium. And these are very important radioactive elements that end up getting used a lot of times for dating the age of materials. So we're going to look at how some of this dating and age calculations take place. So how does that happen? First and foremost, it's important to understand that radioactive decay all takes place by first order kinetics. First order kinetics, what's that? It's something that we spent a lot of time with in last semester, actually earlier this semester in our Chem 132 General Chemistry 2 class. And we learned that there are some mathematical functions that we can use for first order, and I have them down in the bottom right down there. There are two things. There's a differential rate law that lets us to know something about the rate, the speed of the chemical reaction, and that's rate equals K to the N, where N is some kind of isotope, or the concentration there, or an amount, and it's raised to the first power. That's very important. And then the natural log of an initial amount and the amount remaining, you take that ratio, the natural log of it, that'll equal the rate constant times time. Some other interesting things come out of that we can relate the half-life and the rate constant together with this simple equation, and it's actually I'll go little k is equal to ln of 2 over the half-life. And if you rearrange this equation, you can also get T1/2 is the natural log of 2 divided by k. So some very important things there for us to remember as we get into kinetics here. All right, the other part is what with this T1/2, what is this? It's the half-life. And so this is a measure of how long, that's the time that it takes to get to half the original amount. Half the original amount. So we did this in chapter 12 of our work here, so this is good review. So if you start out with 100 milligrams of this isotope that's radioactive, you would have 50 milligrams left over in whatever its half-life is. So this transformation of half-life, we can relate back into a rate constant, which can be plugged into a rate equation or into some equation on time, so we can know something about the age. So this half-life is very important, and it proceeds in the way that first order reactions do. And what is that? Very constant. Every half-life proceeds at the same amount of time. So if, in here we have an example of oxygen 15, and it decays in what? It looks like its half-life is 2 minutes. So in 2 minutes, it goes from 20 down to 10. And then in half that, and then if you double that time here, so another 2 minutes, it goes down another half in amount, down to 5. And another half in the same amount of time. So the time amount is not changing in between them. Now overall, it's been 6 seconds to get all the way, so we got to keep track of the total amount of time that's gone. So what remains after 3 half-lives? So that would be 1 would take you to 10, 2 would take you to 5, and 3 would take you to 2.5 milligrams. And then we could keep going if you wanted to get to 5, and then it would go to 1.25. That's at the 4th one, and then half of that, probably 0.625 or something like that. My math may be, or maybe, yeah, something like that. Anyway, half of 1.25. And I think my number's not quite there. Of course, yeah, it's getting close. So it's half of that number. All right. So these are important concepts that we're going to use when we deal with our problems here. Here's a question for you. How many atoms are in 1 gram of carbon-14? Think about how you would do this problem. All right, you can pause the video, come back. All right, assuming you pause the video, you've thought about it, and now you have a calculation. What did you come up with? Well, hopefully you came up with 4.3 times 10 to the 22 atoms of carbon-14. Well, how did you do that? Well, you need to remember that when we say carbon-14, it doesn't weigh 12 or 12.011. We can assume, and we will use in our class here, that it's meaning 4.0 grams per mole, 14.0. So then if we have a gram of that, we can multiply it and do this Ooh, let's get rid of my thing. We can do this calculation right here where we convert the grams into moles by dividing by and multiplying by the molar mass here. And then, oh, I had it in here twice. I think what I was intending to do here, we can go, so this we don't need. I think we have our pen in here. We can just go right into the number of carbon-14 atoms by multiplying by Avogadro's number. Good, we're gonna need this. When you think about this. All right, so next we have, how do we understand the kinetics? Well, remember we said this was all first order. So what does that mean? That means then we can relate the rate of the decay that is taking place equal to some rate constant times some amount n. Now, rate is kind of an interesting thing that we're going to have to get familiar with for nuclear chemical reactions. And the way that we think about and talk about it is actually in this decay process, that every time the radioactive element decays, it gives off a particle. And we have an instrument called a Geiger counter that can pick it up. So another term for this is disintegrations per time, like decays per second, or it's some kind of disintegration. Disintegration means falling apart. Well, these elements are falling apart. And we can relate it to some amount. And the amount could be the total number of atoms that are there, electrons, alpha particles, the number of electrons or events that are given off. That's what n is. So one event or one disintegration is one atom in this process right here, this carbon-14 is decaying by beta emission and it's given off. So when we use the rate equals Kn, we're often being asked for what's the rate, what's the disintegration in particles per second. So we're gonna need to know something about the rate constant and then how many particles we have there. So let's not forget though that the half-life is related to this rate constant. So half-life and rate constant are really just two ways of expressing the same thing. Well, how does this Geiger counter work? So we can get these rates. Essentially, as the element releases an electron, this can send out ionizing radiation or some other event like a gamma particle, photon will come off. As that ionizing radiation gets inside of the tube that is hooked on to the outside here of a Geiger counter, that ionizing radiation gets in there and it ionizes the particles in there, which causes the conductivity between this inner piece and the gas, argon that's inside there. They put a gas around there. It ionizes that and it causes electricity to flow between this probe here in the middle and the other materials in there. And so you get a click. Click, 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 click. And the more clicks, that's a faster rate. More disintegrations per time taking place. And we can relate the more clicks to the amount of material that's there. So if it's disintegrating very fast, we'd say, oh, that thing has 100 disintegrations per second. And it really kind of is telling us how much is there. Because after a certain amount of half-life that would take place, a half-life, we would have half the amount. So maybe there's only 50 disintegrations or 50 events per second or per time. So we've got to think about the rate here can sometimes be used as an amount. So it can be a bit confusing. And so we want to keep that in mind. All right, alpha particles are sometimes hard to detect because they can't penetrate through these sidewalls to get in and ionize the material. Okay, so I want to keep that in mind. Let's go ahead and erase that before we go on. All right, so this was, you can see a Geiger counter. I blew up the meter, counts per second. Counts per second tells you how much is there based on how fast the degradation is taking place. Very good. All right. There are some assumptions when we do our calculations when it comes to dating and think about that. So we want to understand some of those assumptions. And the first, let's understand some of the variables that are involved here. The rate constant or half-life is K or T1 half, and we can relate those to each other. Do these change for an element? And much of the work that I've seen and read about states that this is a really, really hard measurement property of the material to change. Temperature doesn't seem to change at pressure. Where you find that element, like what other chemicals are around it, it seems to be fairly independent of the material, temperature, and state that it's in. So the rate constant doesn't seem to change for materials when we look at them individually. T is a calculated value typically that we need there. There's really no assumptions involved in that. N is the amount of material that we find when we're making a measurement. So that's typically from some kind of mass spectrometer that will measure the amount of each isotope. And just need to handle the samples carefully so you're not contaminating them with materials that could influence the measurements in one way or another. The N0 is the original amount of material that was in there, say carbon-14 or lead or uranium, these potassium argon dating how much potassium was in there. So the calculations get more sophisticated, but they're often based on this type of an analysis here. So there's a pretty big assumption of how much of a material is originally there, because we can only measure what's there now and then use some properties of the rate constant to figure it out. So this is something to keep in mind when we think about radiometric dating of things. It's not really getting a good feel for what's there originally. So what numbers can be used for the amounts, N and N0? Because this can be a bit confusing. Students are used to moles, maybe mass, concentrations, these kind of things. When it comes to nuclear chemical reactions, we got to open our minds. There can be some other things. You may just see the term DPS for disintegrations per time. So like 7 DPM or 3.5, these are things that you may see. And they're really telling you how much is there, because the greater the disintegration rate, the more the material that's there. Certainly you can use molarity and mass. These are things that we can use directly right into there. But oftentimes, as we'll see in our practice problems here, you're just given a percentage. Hey, we found that there's 20% left over, or degraded by 20%. So you're going to be able to determine a fraction of the material that's remaining. And I should have put N and N0 instead of A and A0 for there, right? So let's not get caught up and not meaning anything different right there. All right. So another thing before we do some practice calculations here is a Curie. See, Marie Curie. She actually has a unit named after her. And there's many of these materials have a lot of disintegrations per second. So it's good to have a unit that can simplify the writing of these numbers when they can get pretty big. So Curie is 3.7 times 10 to the 10 disintegrations per second. So it's a pretty big number. And it's one of the other units you come across is becquerel, Henry becquerel. And it's a BQ. And that is also equal to a 1 disintegration per second. So that's important to understand as well. So here's a practice problem. Say carbon-14, it's a radioactive substance that decays by a beta emission with a half-life of 5,730 years. How many electrons are being emitted per second for a 1 gram sample of diamond composed entirely of C14? Well, whether this is real or not, probably not. But what kind of disintegrations would you expect per second? Now, what equation from the first order rate law and the differential or the integrated rate law, A or B, would we use to do this calculation? What do you think? See, getting started is the hardest part. Once we figure out what our equation is, the problem can kind of fall in place for us. So the question is, how many electrons are emitted per second? Which one would you pick? And hopefully you went ahead and picked A. Rate is equal to Kn. Well, we're going to do that. We're going to use this equation and we're going to see if we can come up with and find the rate here. And I think I have it worked out on the next slide for us to see here. See, this equation right here, B, is really when we're dealing with time in terms of how long did it take for something to take place. Here it's asking how many electrons per second. It's asking a rate. And so we want to get after that and find the rate. But somehow we got to figure out how many particles are involved and the rate constant that's there. Well, we can use the rate constant. I think I'm just going to jump to the next page. I have some of it worked out here, but it's better if I just go to the next page. All right. We can take the half-life that's in 5,730 years and turn that into seconds. Why? Because our answer is asking us to do that in seconds. How many disintegrations per second? So we take the half-life and convert that into seconds using these conversion factors for year to day and day to hour and hour to 3,600 seconds. We can figure out what the half-life is. And then using the half-life to a rate constant relationship, we can then figure out the rate constant. So 0.693 divided by the half-life, and this gives us the rate constant. So remember, we're going after this equation right here, rate equals Kn. So we have just gotten us a K, and this is going to have units of 1/seconds or inverse seconds. So the other part was how many disintegrations per second, electrons emitted per second. Well, we need to then figure out, if we're trying to figure out how many electrons emitted per second, well, this is going to be related to how many carbon atoms I have. Because each carbon-14 atom is going to emit an electron. I should put an arrow in here, so that we have a disintegration for each one of those. So if we know if there's a 1 mole of carbon-14, we're going to know we had 1 mole of electrons. So we need to figure out how many moles of carbon-14 is there. So this goes back to our calculation that we're talking about. How many atoms are there in 1 gram of carbon-14? Divide by the mass, the atomic mass of carbon-14, multiply by the number of particles, and we get the number 4.03 times 10 to the 22 atoms of carbon that's there. But it's also the number of electrons that would be given off in that beta emission. So now we can just plug in those two numbers that are there. Our number of atoms, that's going to be, this is our big N right here. And then our rate K is right up here that we calculated. So we plug in those two numbers and we get the number of electrons per second, the number of particles per second that are decaying, 1.09 times 10 to the 11th. That's a big number. So we could use the Curies here to help us out. And how do we do that? Well, if there is 1.09 10 to the 11 decays per second, electrons per second, these are all the same thing, then 1 Curie is 3.7 times 10 to the 10. This turns out to be 2.9 Curies. All right, let's go work a couple more problems. Radon 222 emits alpha particles. Write a balanced equation to show this process. Whew, let's clear the screen here for us. So we could do that, okay? 222 radon and Rn. And it says it gives off an alpha, an alpha particle, which can be written as a helium atom. And then we've got to figure out who in the periodic table is, let's see, they're gonna add up to 222, and I've got my little one here. Oh, I can't even read it. So I may pull up the periodic table in a second. But whatever it is, whatever X is here, radon is the element. Let's look over here. It's over here by polonium. Yep, definitely need my glasses. Sorry, folks, because I have a really small periodic table. Oh, there we go. 8586 is the element. Here we go. So now this one's going to be 84. I'm going to take my glasses off. And we can now figure out which element is 84. So you just back up, and I believe that's going to be lead. And the mass up here will be 4 less, so 222 minus 4, so that's 218. Good practice on that. So X is lead. Element 84. Oh, polonium. See, I can't read. That was Marie Curie's element that she discovered, 84, and that's where we should know this one, because that is where the dividing line between the stable and unstable elements. How long does it take for this radon 222 to decay to 20% of its original activity with a half-life of 3.82 days? The question I have for you is, which equation are we going to use to figure this out? Pause, and you should really try to think about this and figure it out. All right, so hopefully you've done that, and hopefully you picked B now. Why? Because what are we given in here? How long is the question? That's a time question, which is best answered by the letter T. So how long do you think this might be, approximately? And so you can give a guess here. All right, what do you think? What did you come up with? Well, the answer is 8.9 days. We're actually going to do this calculation right here. and or we can show it and think about it real quick. So 20% of its original activity. So if we did one half-life, which is 3.82 days, that gets down to 50. So if we add another 3.82, this would get us down to 25%, because that's half of the half. So now we're looking at about 7.6 days. And if we go to another half-life of 3.82 days, that's going to get us into about 11 days, but that also gets us to 12.5%. So that's too far. That's too far. So the best answer then is going to be somewhere around 8 days or so, just by thinking through. And this can be a great way to double check your answers. So it looks like I actually have another problem and related to this, but didn't do this exact same one. Okay, so but we can do some guessing on that based on, I would say, educated estimation there. Radon 222, found in many homes, is a potential haphazard and actually believed to account for about 20% of lung cancer cases, 20,000 cases a year maybe because of that. The half-life of radon is 3.82 days. If you begin with 46.8 milligrams of the isotope, what mass remains after 9.24 days? All right, so what equation are we going to use? We got 1 or 2 down there in the bottom right-hand corner. Well, let's see, if they're giving us time, well, they're giving us K, the half-life, this is T1 half. So anytime you're given T1 half, we can know that they're really giving us K. Well, that doesn't help us determine which one we're using. But if you begin with a certain amount, okay, so they're telling us a certain amount, so that's like N0. And then what remains afterwards? Well, this is probably our N, then the number of, or the amount afterwards. What are they asking? What remains after? Okay, that's what they're asking us for, but 9.24. I bet that's time that it took. So what variables have time and N and all these? So this is the second one, the integrated rate law. Well, do I have to convert to molarity or something? I feel like that's what we've had to use in the past. Or can I just use the mass? Well, it turns out you can just use the mass and you can just use it in milligrams. Well, let's first figure out the half-life here, which is kind of what I did in this calculation, 0.693 divided by 3.82, and it gives us K, the half-life. All right, and you'll see up here I use N or A. I apologize for that. It doesn't really matter what letter, we just should be consistent, right? So, and I'm getting this stuff covered up, so I'm going to go ahead and call that one A0, because that was the original amount. And then what remains afterward is A. So we can assign A0 to 46.8 milligrams, and what we don't know, we'll just call X. Plug in this information into the integrated rate law. We've got our K, and then here's A over A0. There is the amount of time, 9.24 days. And when I rearrange this side of the equation, I get a negative 1.676. I can take e to both sides there. So I'm going to erase this stuff, maybe. Clear. All right, and then we can easily see here now, when we take that, I'm left with X over 46.8 milligrams is equal to 0.18. Solving for X, I get 8.75 milligrams. All right. So that's how we use these equations, and there's more that we can do, but it's your turn to go practice some of these problems in OWL. So thanks for joining me, and hopefully we've got some practice thinking about the kinetics. It's all first order, and how to practice setting up these problems and going through them. Thanks for joining me, and hope you've learned a little bit more about nuclear chemical reactions.